SwayamPrabha. Digital India. Educated India.
Now I'll move from there to simple temperature dependence of magnetism. Okay. So you have a material, let's say F electrons you have or D electrons you have, whatever you have. You know at room temperature magnetic moment value is whatever x2, let's say 2 Bohr magneton, whatever it is. You know there is a value. The moment you are cooling it down for room temperature or from a high temperature to room temperature, whatever it is, the moment you are cooling it down, those spin previously you were having now will get an opportunity to realign. Usually molecules means you can have different spin organized in a different fashion. Let's say you have 10 different domain, 10 different metal centers. Those 10 different metal centers are having spin, one up, another down, another up, and so on. It's a mixture of up and down. Let's say it's a mixture of up and down. This is the particular temperature. Let's say this is room temperature or whatever temperature you want. Now you cool it down, you cool down the sample. What will happen? This randomly oriented spin will get some particular orientation. It will try to freeze. You will be able to freeze this spin more and more if you decrease the temperature. You start with 1000 degrees centigrade, come to room temperature, magnetic moment value will increase for the sample. This is the behavior you are expected to see for paramagnetic complex. Okay? So random spin, little bit organized, further organized. Now that's the kind of behavior you should expect for paramagnetic species. Sometime what happens is one spin of one molecule is influencing the spin of other molecule. How it is? Let me give you an example here. Let's say this is a spin, this is the d orbital of one atom or one metal center. This is the d orbital of another metal center. Now, in absence of anything in between, if there is no bridging between these two metal centers, this is spin up, this is spin up, half and half. So total spin should be half plus half 1. But in presence of a ligand or bridging species having 2 electrons, what will happen? This ligand spin will be down, this is up, this is down, there is a bond formation. If this is down, this is going to be up. That will enforce this spin to be down. To start with, you have up spin for this, up spin for that. 2 centers up, up. Since they are bridged by a second ligand, something let's say oxide, O2 minus. It has 2 unpaired electrons. Let's say you have copper 2 plus or copper 3 plus, oxide, copper. Copper 2 plus, oxide, copper 2 plus. Copper 2 plus is D9, 1 unpaired electron. Oxide, 2 unpaired electron, okay, 2 unpaired electrons, and then another copper 2 plus, another unpaired electron. Let's say you are having copper, oxide, copper, 2 plus, 2 plus, 2 minus, there is net charge is going to be let's say 2 plus, doesn't matter. Now this is a D9 electronic configuration, this is a D9 electronic configuration. One spin up, one spin up, one unpaired electron, one unpaired electron. Oxide is having two unpaired electron. What it is making it, essentially, since this is a coupled species, this spin or this copper is bonded with oxide, this oxide is also bonded with that, this will enforce this up spin to go down. So this is copper spin, this is your oxide one spin. That will mean that this will go up and this spin will go down. It is spin pairing. They will try to pair it up. So up, down, up, down. Overall, although it's a D9 electronic system, it was supposed to be paramagnetic. Unpaired electron means it is paramagnetic. Net effect is due to these exchange, it will become diamagnetic. Okay? So what I am trying to tell you is that knowing the whole thing is important. Just individual metal center is not good enough to tell the bulk properties of the compound or bulk properties of the material. You need to know what they are bound with, how they are bound with, are they communicating with each other. Okay? So it's a very interesting phenomenon. You can see the magnetic properties can be communicated. If it can be decreased, there is other orientation where it can be increased by having some interaction. So both decrease and increase is possible, right? So this is where what actually you see kind of this antiferromagnetic behavior. You see it is after certain temperature you can see the magnetic moment value is decreasing. So because they are interacting after that temperature, they are interacting with other molecule in a way that will cancelling some of the spin. It could also increase as you see for ferromagnetic cases. So it is nothing but electronic spin are varying different ways, okay, with respect to temperature. It may be pairing up or it may be getting more unpaired. Okay? Thereby you see, of course, this is nothing but more of a paramagnetic, but the increment with respect to temperature is huge all of a sudden, right? So it is increasing as you decreasing the temperature, but after certain temperature you see that there is a jump or the slope is changing, right? So something is happening in terms of electronic arrangement. That's all it says. Okay? Now you can see read about these of Curie temperature and whatever, this nil temperature and so on. I think you have studied it before. Ferromagnetic, antiferromagnetic and paramagnetic. You study from a book. Okay? Magnetization. Okay? So if you see, if you are trying to magnetize one species, let's say with a magnet you are trying to magnetize another species. What essentially happening is you are reorienting the spin of those molecules. Okay? So for example, this is the magnetization. If you can reverse the spin, this is going to lead to the neutralization. Right? It's nothing but changing the spin. All up, all down, one up, one down. How many up, how many down? Going to determine the magnetic properties or magnetic behavior of a compound. 2 more minutes, maybe 1 minute will be good enough. Okay, you read this. Okay, there is some material. Okay, for example, over here, if you are increasing the temperature or decreasing the temperature, you can understand how you can give low spin to high spin. You know that if you heat it up, for example, you can go from low spin to high spin. Spin will increase, right? So if that is happening, you are going to increase the magnetic moment, right? So you are increasing the temperature and at certain temperature high spin complex will be forming. From there low spin to high spin complex is formed. Now if that high spin species upon cooling down or bringing it to room temperature does not come back to the previous orientation, that means low spin orientation quickly, those are the one are called hard magnet. You can heat it or you can change the external condition, you can keep it in a high spin state and it can hold on to that magnetic behavior for some time. Those are hard magnet. Usual magnets are hard magnet. There are soft magnet. You heat it little bit, it goes up, magnetic values goes up, low spin to high spin configuration occur, but then again cooling down, it comes back very quickly. These are called soft magnet. So you can read about hard magnet and soft magnet once again from any book. Okay, almost done. I think this is done. This is one or two last slide. It's the same thing. So we have learned so far hard magnet, soft magnet, antiferromagnetic, ferromagnetic, paramagnetic. Now if you have a cluster, for example manganese oxo cluster, manganese can have spin, oxo can also have spin, manganese 2 plus let's say, oxide 2 minus, has unpaired electron. Overall you have lot of spin up, lot of spin down. Theoretically then you have to do almost a calculation in computer to figure out the net magnetic moment of the species. Alright, I think that's all for today.